Good afternoon, everyone. So I would like to welcome you all to this Forum 360 on certification of AI-enabled systems. So I'm Umut Durak. I'm working for the German Aerospace Center, DLR, where I lead the research on avionics systems. Additionally, I'm a professor for aeronautical informatics at the Closed University of Technology. Today, I'm excited to facilitate our discussion on this important topic. How can we certify AI-enabled systems? Or as I like to phrase it, how to fly artificial intelligence. So AI has been around for over 80 years, right? So the difference today. So we have the compute power that truly allows us to unlock its full potential. Think about the NVIDIA Project Digits that has been announced last week, I believe. So with $3,000, you can buy now a computer that you can do your inference with models with more than 200 billion parameters at home. So with this power, we can implement new techniques that performs in ways we couldn't have imagined for a few years ago, right? Just like many other fields, we all in aviation are eager to leverage what AI has to offer. But let's be clear about what we mean when we talk about AI in aircraft today. So our particular focus is on learned AI implementations. What does it mean? This involves using machine learning techniques that have been developed through offline training. Offline training is the key for the AI technologies that we're discussing today for aircraft. So where do we envision using AI? So we see the opportunities to compress our lookup tables. Think about the applications like ACAS-X to enhance our computational performance for things like optimizing routes or implementing better performing functions for prognostic like anomaly detection. And it gets even more exciting, right? So we're exploring complex applications like natural language processing in cockpit, or computer vision for runway detection, for autoland, or sign detection for autonomous taxiing. However, we must keep in mind that aviation is one of the most strongly regulated industries in the world. So therefore, certifying AI-enabled systems is the critical step forward. So to put it simply, we need to ensure that these AI systems are safe, reliable, and the most importantly, compliant with the regulatory requirements. So this is not solely a technical challenge, it's a challenge for industry, it's a challenge for academia and the regulators. So we must work together to develop the new standards, or the standards, the guidelines, the ways that we can enable the safe adaptation of AI in aircraft. So accordingly, today we have representatives from industry, regulatory bodies, academia, and research and development agencies with us on stage to discuss the certification of AI-enabled systems. As we dive into our discussion, I want to encourage you all to participate. So your thoughts, your questions, and your concerns are what make this conversation valuable. And as this is not the first 350 forum of the conference, you all know how to participate, right? In a couple of minutes, I will ask each of our panelists to briefly introduce themselves, share their journey in AI-enabled systems, and explain their motivations for joining today's important discussion. But before doing so, let me share a bit of my own journey. Back in the late 2010s, DLR made the strategic decision to embrace artificial intelligence in safety-critical domains. We initiated several research and development projects, along with establishing a brand new institute for safe and secure AI. That's when I became involved with the international committee SAE G34, working on developing standards for and guidelines for AI in aviation. I later even co-chaired one of its subgroups on AI implementation on avionics systems. In the past 5 years, I participated in a number of research projects for safe AI integration. What I've learned is there is no silver bullet. no single solution that fits all. The challenge posed by a small neural network may differ vastly from those presented by a complex AI perception stack. So I'm eager to hear the diverse strategies and insights on certifying AI-enabled systems that our panelists will share today. And I truly hope by the end of this conversation, we all feel confident that certifying AI-enabled systems is not a bridge too far, maybe not for all of the use cases, but some of the use cases at least, it's a bit of a grind. So with that, please join me welcoming our panelists, Dr. Wasson from Joby, Dr. Koffer from Collins Aerospace, Dr. Valquez from DARPA, and Dr. Pam from FAA. So would you briefly introduce yourselves, your journey in AI-enabled systems, and explain your motivations in today's discussion? Please.
Can you all hear me?
Yeah.
That sounds good. And I'm going to peek down there because we have a clock so that I can stay within my 5 minutes or so.
Yeah.
Okay, perfect. So hi, everybody. I am Kim Wasson. I am, as it says up there, Staff Development Assurance Engineer at Joby Aviation. I'm also the Autonomy Certification Lead. For those of you who are not familiar with Joby, we are a started up. We started in 2009. We are deep into certifying our all-electric vertical takeoff and landing aircraft. And we are 3 stages in and looking at hitting TIA this year. So we're quite far along in the civil aviation certification type design process. And that brings me to my first point that I want to hit on is that type design process. This is my first time at AIA, at AIAA SciTech. I've had a paper here before, but somebody else delivered it for us. So this is my first time meeting with all of these people in this environment all week, and you get a feel for the different populations that go to different meetings, and I'm hearing a lot of really exciting developments, really bleeding edge, lots of promise, lots of potential, lots of exciting new research and far out R&D stuff. And one of the things that I want to bring out is that that is all necessary, and then in order to get it into production systems, there's a whole technology transfer process that has to happen. And so, as Umut said, certification of civil aviation aircraft is highly regulated. We have a whole set of regulations that impose demonstration that we meet safety intent onto this entire engineering process and product, because we're going to put our families on these airplanes that are going to fly in the airspace. So there's all of the R&D that's needed, but then it's got to be brought to an actual production development and assurance process. And so that's where I live. I work at Joby on an actual system in development that's going up for certification. We are pre-revenue, and this brings me to another point, which is that before I came to Joby, I worked in a lot of applied research. I did a lot of collaboration with agencies. Coming to Joby, one of the educations I have received is that if you are pre-revenue and you have to reach certain milestones in order to stay alive, it becomes existential, that you have to focus on what that assurance burden is in order to deploy as a commercial operation. And so that has allowed us to develop a very clear handle on what that assurance bar is to meet the safety intent of the regulation, to know that the product we put out meets all of those bars, not just because we threw everything in the air and have a ton of margin, but because we know and understand exactly what those bars are, and we're hitting them strategically and intentionally. So that necessity is the mother of invention thing, working in a pre-revenue company forces you to make sure you understand a whole lot of specifics about what's required. And then on to what's required. I work on the assurance of emerging technologies. So we're putting things on this aircraft. A lot of this aircraft is very conventional. I mentioned I'm the autonomy certification lead, but our first type cert intent configuration is conventionally piloted, right? So why am I there? Because we understand that increasing autonomous function on a system that's going to operate in the national airspace is a long lead time challenge that requires not just all the R&D, but all of the policy making, all of the socialization, and all of the certification support process of explaining and demonstrating and agreeing with the regulator, with the approver of your system. And so thank you. They threw my title slide up there. I'm actually off-roading. I'm going without the slides. If I need the slides later, I'll bring them up. So Umut asked us, what is our connection to AI? My connection to AI is that it's an emerging technology that we don't yet, for production systems, have all of the stuff we need to assure them to meet the safety intent of the regulations to fly these things in national airspace, other than for very low criticality or very simple applications. But we have some good strategies and some good ideas on how to get there. And I don't know how much of my time we've used, but we're going to open this up over the course of this.
That's
so
true.
I'll stop there for now, and I'll hand it over to Darren. You can have the clicker if you want to use the slides. I don't know who's advancing slides, but you can just skip mine and go right to Darren's. And if I need mine, I'll pick it up later.
Yeah, I know. Yeah, way to go, Kim. I'm Darren Kofer. I'm a fellow at Collins Aerospace. Collins is part of RTX, which includes Raytheon and Pratt & Whitney. And Collins, as a company, makes everything you need to build an airplane except for the wings and the metal tube. So all the cool, fancy controls and displays up in the front of the airplane, and the networking gear, and the radios, and even all the stuff that you hate about airplanes, like seats and toilets and galleys and stuff like that. I work in the research organization, which means I both work, in industry, but also engage with research organizations, funders like DARPA, and also with the FAA on certification concerns. My background is primarily in control theory, and then from there into assurance of high-integrity software systems. And that was really my excuse for getting involved in what's happening in AI and ML. So not so much from the learning standpoint, but from the assurance standpoint. Not the I believe that we can do all kinds of cool, amazing functionality with machine learning and neural networks, but what I care most about is the assurance questions, and how do we know that there will be no surprises during operation. So the things one of the main messages I want y'all to take away from this is, we don't want to go into the ditch on either side here, right? There's a bunch of people that think, hey, neural networks, it's just software, right? What's the big deal? And on the other hand, other people have the mindset that, why would you put, AI into a safety critical system? That's crazy. And confession, that was me on the right there a few years ago. Why would you ever put, machine learning, something that is different from our traditional ways of developing and assuring software, into a safety critical system like an airplane? And what I have come to see is that there is a way that can be done. There are technologies, there are assurance tools whereby that might be the preferred solution. In some of the cases that like Umut mentioned, we're not even doing super crazy autonomy functionality, but we're doing very mundane things, implementing gigantic lookup tables, which take up a lot of resources, and embedded platforms, which an airplane is an embedded computing platform. You can do that much more efficiently by training a neural network. It's very small, very compact, to do the same nonlinear function that you were implementing in a lookup table. So there are actually other really good reasons that you might want to use machine learning in addition to advanced autonomous functionality. So you know, what are the concerns? Why is this not super easy? One of the main objectives when we go through the assurance processes and certification is to identify and eliminate unintended functionality. So this, you know, Twitter post here is, you know, the Tesla behind some dudes on horses in the drive-through line at the Whataburger, and it has no idea what it's seeing. Is it a really tall person? Is it a giant dog? Doesn't really know what it's seeing. All right, so that's kind of funny, but we've all seen less funny incidents where this kind of uncertainty leads to accidents. That's what we can't allow to happen in the aerospace industry, especially the civil air transport industry. And this comes about because of, you know, if you haven't trained on everything that you might possibly encounter during operations, you can't. The input space might be too big. It's, you know, for visual systems like this. How do I guarantee that there's not going to be some unintended functionality? So what this means is that on the right here, this is just a picture of what some of our processes, our certification processes look like now. Machine learning actually is where this red arrow is. How do I get from system requirements to a model that then I can go and implement? And how do I know that that model doesn't include extra unintended behaviors? For traditional software, we have really good, really reliable ways for demonstrating that. For machine learning, we have to come up with something different, new processes, new technologies. That's what the research in this area has been about for the last 5 years, say. So where does that get us to? You know, I like to put some of our applications on this grid of criticality versus complexity, and you can see this is a log scale on the vertical axis of the number of parameters in the system. So a lot of the stuff that we're talking about is very simple. It's down in the bottom, you know, hundreds, thousands of parameters, and a lot of the stuff that we want to do is low criticality. This green block, the number one. These are things that we can go and do now and get approval with, and those are the kinds of things we're working with the certification authorities on getting approval for now. But everything on the bottom half here, to be clear, is offline trained supervised learning, right? That's all that's really that we're talking about for, you know, really the next, you know, 5, maybe 10 years. Moving beyond, you know, for higher criticality systems, we're going to need to use some of the new formal methods-based analysis tools to be able to prove that there's no unintended behaviors present in systems that we want to use in higher criticality applications. The yellow area, number 3, those are the vision-based systems where you actually might want to do very safety critical things with using a perception system. We don't have answers to that now. Our verification tools don't scale up that far. So, you know, you might be able to apply runtime assurance, monitoring, architectural mitigations to essentially lower the criticality of the machine learning component that you're talking about. But that's where a lot of the work is focused right now. And then way up on the very top is all the generative AI, LLM stuff that everybody's excited about now. That is, you know, that's not anywhere close to getting put onto airplanes. You know, that's things that we might use, you know, for making software development more efficient, but not being considered now for online, onboard, airborne applications. So, you know, echoing what was said at the beginning, there's not any one-size-fits-all solution. We've got a lot of different approaches that we need to use depending on the complexity and criticality of the system, and that's where all the new cool research comes in. Over to you.
It's a great segue. Am I audible to everyone in the back? Good. Yeah. First of all, thank you for the invitation. This is my second panel at AIAA. Happy to be here. My name is Alvaro Velasquez. I am a program manager at DARPA. For those of you who don't know, DARPA is Defense Advanced Research Projects Agency. We're sort of the risk-taking arm, which I know is a cliche to say, but we really do take sort of the big risks, high payoff programs for the Department of Defense. Most of my programs have been on adversarial AI and autonomy, which a lot of people don't realize are actually two very related fields. And my original journey into this kind of certification of autonomous systems really started before I went to DARPA. So I've done a lot of research, I've published a few papers on verifying very basic perception systems, verifying reinforcement learning, sequential decision-making systems. And that's where I came to realize that we're very limited in the kinds of things we can certify when it comes to AI. And so I think it's worth asking the question, sort of where are we now technologically in our capabilities to certify AI systems, and where do we want to get to, right? And so where we are now, as I see it, is that we're good at verifying very small AI models, nothing anywhere close to the famous LLMs and all these other models that we know. We can verify them for very simple properties, typically robustness and safety properties, not general properties that we would want to verify. And we can, this is the critical piece, I think, we can verify them or certify them for very unrealistic threat models. This is really the big problem. So I can give you a very simple example. If you're trying to verify a perception system, you typically have some image or video. You define some budget on how much you can perturb each pixel, right? Mathematically, what we would call an L infinity norm. You take your AI model, you take your robustness property, and you say, will this model still output the right action or the right detection given those perturbations in pixels? All kinds of really cool methods there. But the problem is, if I were to change the color of Darren's shirt, that's already a huge perturbation that a lot of these models can't account for. If you introduce a new aircraft, if you introduce changing weather patterns, these are enormous perturbations when it comes to those threat models. And so I think it's encouraging the results we've seen in the certification of these systems, but realistically, I don't think we're at a place where we can really certify specifically perception-based systems, but even more broadly, autonomous systems. Because what is an autonomous system? It incorporates the perception module, how that perception module interacts with the high-level decision-making module, what we typically would call the planning module, and then how the planning module interacts with the low-level controllers. At a minimum, you have these three things. And so the question then is, how do we properly scope down the problem space of certifying AI systems? I think someday we will get to the point where we can actually certify these very complex autonomous systems. But in the short term, I'm very encouraged by what we can do with things like low-level control. We've seen, for those of you that are interested, there's a line of work called Deep Reach, which looks at how you can verify low-level controllers subject to safety properties. I've funded some of that work myself, and we've gone from 48 minutes to verify very simple safety properties to just milliseconds. So we're at a place where we can already rigorously verify low-level controllers without the perception. That's already tremendously useful, right? We don't have to kid ourselves and say that we're going to certify everything. We have to be clever in what we choose to certify. So that's one direction. Another direction that I'm encouraged by is actually sort of the complementary direction of using AI to certify. So there's a certification of AI, but there's also the use of AI methods to certify systems, because a lot of the classical sort of mathematically rigorous ways that we like to certify systems are very slow, right? They depend on things like SMT solvers and other very expensive methods. And AI is actually very good at accelerating those processes. So I think this might be a direction that needs more focus, is that converse direction of AI for certification. And I'm happy to get into more details as we get into the Q&A. Thanks. Yeah. Was I the only one without slides?
Good afternoon. My name is Chung Pham. I am the chief scientist of AI and machine learning at the FAA. And as you know, at the FAA, we do certification of aircraft. So that's the end of my introduction, but since I was given 5 minutes to do it, so I would like to ask you for permission to share some of the work that I did at the FAA. For the past 2 years since I joined the FAA, I was given a job to do a roadmap that create a path to certification of AI products. So for the past 2 years, we developed this with the consensus approach with the industry to create the path, and we identified 3 different components in our roadmap. One is the application domain, where we begin with the onboard software. The second one is the guiding principle, the thing that will be guiding us to create the path to certification. And in the background, we do have supporting research. Now, as you know, AI system is not going to be a simple system, and we are not going to do certification manually. So we are looking at using computer to help us to analyze complex systems. So that's the important thing about supporting research in the background to help us to move forward. But I want to mention 2 main guiding principles that might be applicable to the discussion today. One is we try not to personify AI, and the reason is that we have seen a lot of discussion of AI, and some of the discussion was somewhat misleading, pointing to the direction that it might function or behave like human, and that threw us off for a few years trying to find a way to certify something that is similar to human, when in fact we are still dealing with AI system implemented as software in a traditional computer. So at the end, we decided not to personify AI. So here is an example. When we talk about AI, people talk about machine learning, and you might have seen people explaining machine learning in the context of human learning. So here is an example of human learning that I copied from the movie The Matrix, where they train this main character in The Matrix, and you see that in the general, he see everybody is wearing black, except one person is wearing red, so he got distracted. And a lot of time we worry about that, and in terms of software, you might have heard people talk about unintended behavior, where the software is doing something unexpected. And this is one scenario where it can happen if we look at the machine learning result as understanding that it will be similar to human learning. But in reality, machine learning is just an optimization process that we use and implement it in a computer, helping us to calculate the parameter of a model. And that process we call is a training process. But in this definition, I ran into a lot of trouble with people when I said just. And a lot of time people got angry and they kept defending that it's more than that. And the conversation got distracted, never got to the point that it's not human learning. So I talked to many people and they told me just delete that just, and everything should be okay. Thanks to my counterpart from the UK CAA, I deleted that from my roadmap. The main idea of optimizing is we define the residual errors. This is following traditional modeling, because at that point, all we have is what we call expected output. In terminology of machine learning, people call that a label, and we just try to minimize what is the actual output of the model that we are training with the expected output that we are giving it as a reference during the training. So the modeling technique will fit the model to the data. This is the technology we had for the past over 50 years in modeling. It just got now with the advancement of computer technology, we have fancier and more complex model with many parameters that require complex software to accommodate the calculation of those parameters. So here is an example of modeling that we still follow in machine learning, even though this is a simplistic visualization of modeling with one dimension. We have data here, and what we do is that we find a model, something that is easier to express, but it can somehow represent the data. And in this case, we are showing a linear regression as a model, but the concept is still the same. The model will represent the data. Here is a scenario when we have an outlier, what that I show in the Woman in Red clip of the movie Matrix. So if we put in an extra point, you will see the modeling will be shifted just a little bit, but not enough to treat the special case the way we learn in the human learning. We learn to generalize what we saw, and at the same time, we remember the special case that we have special treatment. So that's the difference between machine learning and human learning that I like to call out. The second thing on our roadmap is that we like to show that at the FAA and at every certification authority around the world, we have a set of regulation that has been ensuring safety for the past many years. So there's no reason for us to reinvent everything just because we have a new technology. So the guiding principle is to use as much existing guidance as possible. And as you saw in the modeling technique, even though the technology might improve with advancement in technology of computer and software for training, but in the end, it is still a piece of software that we are running. So we like to see that piece of software as an engineering component in an aircraft, and we have a huge set of regulation that maintains safety for the aircraft with software. So this is not something new that we are dealing with. So go a little bit deeper into artificial intelligence. When I developed the roadmap, I discovered that we have many different versions of what is AI. So I began by looking at the traditional definition that I learned in class 40 years ago. So it's just a discipline that is mimicking the human intelligence at computational level. So right now, the evolution of the definition is showing more understanding of what is human intelligence that is mimicking, but at the same time, from our certification point of view, we still see that implementation at this computational level is still applicable. So in the end, no matter how well you train it, you get a model, you implement it in software, and you run that in the computer. So that's where we look at in the certification point of view. So what is human intelligence? We have, again, many different definitions, many different examples. The clear definition is showing through example that you might have seen in the executive order on AI, showing what tasks that the AI intelligence can do. So here we want to show you about the problem solving is one of the main characteristics of AI. When we were young, we learned mathematics, and we learn how to solve problem. And if you remember, we begin with some simple problem, and we continue with another simple problem to solve, and the teacher would show us is how to get to the solution. So we got the pattern, and at the same time, we remember those specific problems that we learn, simple problem, but we learn many of them, and once we master one grade, we move up to another higher grade, and secondly, the class begins with some more complex problem. If we jump right into the complex problem, we might be lost. But if we remember what we learned the year before, we say, aha, this bigger problem is consisting of many smaller problems. If we can recognize that and partition them into smaller parts, by the end, we might see the remaining part that might not see before, but it remains so simple that it's very easy to solve. And at that point, we don't know how people solve it, but through intelligence, they know how to recognize a simple problem and structure through improvisation, for example, and solve this simpler problem in the context of putting together smaller problem for a solution of a bigger problem. So this is the idea that we are teaching our kids from grade school up to learn how to solve problem. So the moral of the story is that as AI practitioner, what we want to do is we should take advantage of our understanding of human intelligence and use it to our advantage. And in this scenario, we're looking at a very well-known strategy called divide and conquer. And what we are looking at in the path to certification, which is a bigger problem, we try to divide that into smaller problems at item level, system level, and aircraft level. So if we could partition that to smaller problems, what we see is that we already have many regulations and guidance for smaller parts. The only thing that is left is the verification of the artificial neural net model that people develop. They might develop through different techniques that they show throughout this conference and many other conferences, like deep learning, like reinforcement learning, but in the end, it's the artificial neural net model that they present and implement in the form of software that we have to certify. So that is our approach for the path to certification. So thank you very much for listening to my self-introduction. And here's my contact number.
Thank you very much. Thank you very much for all the panelists for the insightful introduction. So I would like to go to the questions round. The first question will come from me. I would like to turn to our panelists from the industry, Kim and Darren. Let's start with you. What AI-enabled systems or functions would you like to address first, right? So we talked about step-by-step, divide and conquer. We have the simple and the complex problems. So where do you like to start, and what challenges and what showstoppers are you currently facing certifying these systems, and what is the game plan? What is the roadmap of industry?
So I hear this question, and it's what functions or what applications do we want to start with? And naturally, people want to jump in with perception or monitoring or control or this or that. And I don't think that way in terms of the application. I think in terms of what do we have to demonstrate regardless of application, and which things are most ready to demonstrate given what we're already capable of. And so to explain that a little further, I need to back up and make clear for you what certification is in the civil aviation context. And so Trung and Darren and Alvaro, they've all referenced that there's a set of regulations that we're beholden to. Like I said, I work for industry. I'm in a commercial organization that is going through type certification. In order to get approval to produce and deploy our product, we have to demonstrate that our product meets the safety intent of the regulations. The legal recognition of that is what certification is. And to get there, we have to show compliance. We have to convince the approver, among other things, that we meet the safety intent, which includes that if anything goes wrong, we can continue safe flight and landing. We have to show that we can put the airplane down safely, no matter whether it's machine learning or something else controlling whatever function is helping me aviate and navigate and communicate. So machine learning is one implementation choice for the things that go on in the airplane, but ultimately what I have to show is that I meet the safety intent of the regulations. Now that's harder and easier depending on what implementation choices you're using to fulfill which functions at what level of rigor. And the level of rigor is commensurate with how bad it can be. If something breaks, right, there has to be a logical and inverse relationship between how bad it can be and how often it can happen. And to Darren's point about unintended behavior, this is the crux of our problem with machine learning, is we don't yet have general purpose methods to show that the use of machine learning as an implementation choice is going to give us the behavioral predictability we need in the function it's providing for us to say, okay, we accept that and we're going to let it fly, because we can't then argue that we're going to be able to continue safe flight and landing if this thing breaks. Now, this is why we need to look at lower criticality functions to start. And again, to points that some of my co-panelists have made, it's not that we can't do anything yet, it's that we have to constrain what we do, not by what the function is, but by how tractable, how tenable it is to demonstrate that we can do it. And so some of the candidates there then for which functions are things like, what is simple enough that we can understand its behavior comprehensively? So it could be machine learned, but it could be a small enough network that we can manually inspect it or something. Now that's not ideal, right? Because it doesn't scale. So it could be something that is low criticality enough that even if it breaks, even if we can't predict it, it's going to be okay. And that's kind of ideal, because we want to do things where we can observe not just how it's working, but how it's breaking, because that teaches us. That's why we want operational experience at low criticality. And then even there are some bespoke higher level criticality applications that a number of organizations are working on, where they have the logic for their specific application. And you can do that with FAA. You can negotiate an issue paper that will let you use this machine learning implementation choice to provide this function in this higher criticality situation if you've negotiated the logic. But what you need is you need the argument underneath that says, I believe that I can predict sufficiently how this is going to behave such that it meets the safety intent of the regulations, so that I and the approver are going to agree and they'll sign off and I can put this into deployment. But that whole argument has to come together. And in the general case, we can only do that so far for low criticality functions, for very simple functions. But putting those into deployment, getting the operational experience with those, is how we generate the experience and the knowledge in order to see how they behave, how our predictions fare, how we can validate and verify these, so that we can make better predictions and bring up that defensible baseline for what we can assure and deploy over time.
Thank you. Aaron, maybe?
So Kim has mentioned certification. A lot of what we're doing right now is based on gaining experience and both with us and with the FAA in what it will take to gain approval for systems that contain machine learning-based functionality. For traditional systems, we have approved means of compliance with the airworthiness regulations, where that FAA in the US, for example, has said, if you follow this standard for software development, software design assurance, the RTCA DO-178C that you may have heard of, then that you can use that as a way of gaining approval as a means of compliance with the airworthiness regulations. However, for anything that contains machine learning, FAA has said, no, you can't do that. We essentially have to do it on a case-by-case basis. For now, we're working on new standards and new processes for the future. But for now, to gain experience, we're picking strategically particular applications. So I'll tell you three real quickly. One is application for recommending to the pilot what is the most efficient altitude that they should fly at for fuel and time cost efficiency. It's just a recommendation. It's design assurance level D, if that means anything to you. It's just a number, goes on the display, pilot can use it or not. They have to call ATC and get approval to fly at that altitude. So it's both simple and low criticality. So it's a really good starting point. The reason we're using a neural network for this is that it's more computationally efficient. The way you would do it now is a very complex first principles optimization problem, which might be encoded as a giant lookup table. So that was our first application that we took to the FAA, and we got approval for a means of compliance. This is what alternate processes we would follow in order to put that on an airplane. The next thing we are working at is also low criticality, but it's more complex. It's a camera-based system that's supposed to detect fatigue in pilots. Doesn't add anything, doesn't change anything to current operating procedures. It's just basically a warning system like you might see in a car that says, hey, the driver looks like they might be, based on their blink rate or something, a little more, starting to get fatigued. So this is something to enhance safety, but we're not relying on it for safety. So that's a more complex system, but it's still, because of the way it's used in the cockpit, it'll still be DAL D, low criticality. And then one of the next things that we're looking at will be a fuel measurement system that uses some new sensors, and it turns out the best way to process that sensor data is through a neural network. Super simple, just takes a handful of floating point inputs, no vision or anything like that, but it will be higher criticality. And there we will likely be applying some of the new formal methods-based analysis tools in order to guarantee that there is no unintended behavior. Because as far as showstoppers, that's what it is, unintended behavior, to be able to show that. Another way of thinking about this is how do you know that you've tested this system enough? What's your stopping criteria? For traditional software, we have very good structural-based coverage metrics that give us a stopping criteria to help us know that we've tested this system enough to have confidence that it's going to do what it's supposed to do and not do anything surprising. We don't have any except for these small networks that we can analyze. That's really one of the things that we're looking at. How do I know when I've tested this thing enough? Traditional statistical measures don't give us the level of confidence that you would need for a higher criticality system that needs to go through thousands and thousands and thousands of flight hours without a failure. That's really the showstopper right now. How do I know when I've tested a complex machine learning-based system, how do I know I've tested it enough to have confidence, the necessary level of confidence that nothing bad's going to happen in flight?
Thank you.
Can I add a point to that?
Yeah, please.
So everything Darren said, and also for some applications, there might be a firm wall where we might never be able to test it enough. Depending on the complexity, depending on the application, it might be infeasible to get enough data to train the network on or do enough performance testing after. It might be infeasible. And so it raises the necessity that we have to consider things like resilience and fail-safes and et cetera.
Architectural mitigation.
Right, exactly.
That's right. Yeah, thank you very much for the insights regarding the priorities and challenges from the industry. Now I would like to turn back to Alvaro. So I'm sure you encountered a variety of perspectives from industry as a program manager in a research and development agency. how R&D priorities are shaping up. So I would like to ask you, what are DARPA's roadmap for safe and certifiable AI?
Yeah, so DARPA as a whole doesn't have its own roadmap. You know, each program manager, they define their own portfolio of programs. And so I can speak to my portfolio. I think when it comes to certifying AI systems, I'm not convinced that we should be doing the certification directly on the AI model itself, right? These are fairly opaque models. It's billions of parameters that are just numbers that are really hard to make sense of. And so, like I said, we do have mathematically rigorous approaches to verify them, up to maybe 10,000 parameters and very simple properties, very simple inputs, very simple threat models. So I think the way we get around that, and what I've been investing in my portfolio, is how can we extract semantically meaningful representations from these models? How do you take the parameter space of these large models, find the right symbolic representations that we know how to certify, that we've been certifying for, decades? That can be, the knowledge graph representation that captures the semantic relationships across entities. It can be the logic of the neural network. It could be the PDEs that govern the dynamics of how the system evolves over time. It can be many different kinds of representations. And I think there is where we will be able to overcome the scalability limits of current AI model verification. It's a very hard problem, though, because typically when you think about these semantically meaningful representations, they tend to be discrete and non-differentiable, things like logic, for example. But neural networks are continuous and differentiable, right? If you look at the loss function of a neural network, if you look at the optimization landscape, as Trung was mentioning, those are continuous spaces. So then there's a big fundamental question here of how do you reconcile the discrete non-differentiable with the continuous differentiable in order to extract the meaning out of these AI models. Once you have that, we have very good classical techniques that we can employ. So that's part of my answer program, Assured Neurosymbolic Learning and Reasoning. And Darren actually has done a lot of good work in that space under that program. So that's the first thing. The second thing is, in some sense, a much harder problem, I think. And I think Kim actually alluded to it. The fact that we don't have enough data and that it's hard to test enough, how do we typically get around that when it comes to autonomous systems? It's typically through simulation, right? But the problem with simulation is that we don't really know how to simulate things perfectly, for one thing. Second, the way we model a lot of our simulation, things like turbulence dynamics, for example, it's very expensive. It takes a very long time to run the simulation, which means you can't generate the volume of data that you would want to train an AI system. And so there we face a few very big challenges. First is, how can we accelerate simulation? How can we make it so that we can simulate enough data to train reliable AI systems? And actually, the physics-informed machine learning community has made tremendous progress in this space. They've significantly sped up by 3+ orders of magnitude how quickly you can simulate turbulence, fluid dynamics, the deformability of objects. And so I'm very encouraged by that direction, and I think in the coming years, it's that physics-informed machine learning that will enable us to scale up these autonomous systems. So that's one thing. But I think really the bigger problem when it comes to certifying something that you simulated and then want to deploy in the real world is the fact that the real world, from an AI perspective, is an out-of-distribution problem. In AI, we love to talk about, LLMs. They're so great at generating new text or generating new code. But not really. Whenever you generate a new piece of code, relative to the internet scale availability of code data, it's an in-distribution problem. The code is very similar to stuff you have encountered on the web. When you have physical AI, you don't have that luxury. It's an out-of-distribution problem. And this has been the bane of the existence of machine learning since its inception. We don't know how to generalize to out-of-distribution problems. LLMs give the impression of doing so, but they're actually not that good at out-of-distribution generalization. And so there are some very fundamental problems that we need to solve before we can certify systems from simulation to the real world outside of very basic problems like Kim alluded to and like I alluded to earlier with regard to very low-dimensional controllers. So I'm not hopeful that in the next few years we're going to crack that problem. I think we're missing some fundamental advancements in AI before we can crack that problem.
And to close it to civil aviation regulation, failure to appropriately generalize out of distribution is one of the sources of unintended behavior.
Right.
And if you don't have behavioral predictability of your aircraft, you can't meet the safety intent of the regulations.
Completely agree, yeah.
Thank you very much. And with that, I would like to turn to Trung, as a representative of the regulatory agency, right? So what type of AI-enabled systems are you expecting to certify first? Can you share insights on the FAA roadmap for this expectancy, what is coming as first and what will follow? What are the current barriers and showstoppers again you see that might hinder the progress in certifying these systems?
Well, when I came to the FAA 2 years ago, I was facing this exact question, what should I do first? And I tried to begin by looking for simpler application so that I can go through the process of verification. That is the first step in the path to certification, to verify that the system is doing what it was designed or developed to do under specific domain. And I was trying to do that, try to prioritize what should be done first. And the common sense approach was saying that we should look at the simpler problem. But my boss came in and said, Trung, you don't have the luxury of deciding which one to certify first. Whenever the industry apply for certification, we have to handle them as soon as they put in the application. So that has been our philosophy at the FAA, and I'm just following the traditional philosophy at the FAA. But we do see different application in AI, like Darren mentioned. They put in some application not just for getting the approval in the certification, but also to help us to prepare ourselves in terms of seeing new technology. That's one approach that we saw from Collins. Some other company, they brief us extensively behind the scene where they could review everything they did to prepare us to go forward with the path to certification. But in the end, what we saw is that certification requires verification that the system is doing what it should be doing. Since the system is so complex, we have to use computer to verify the functionality and the unintended behavior. With computer, we have to do that. And with computer, just like every other piece of software, we don't really care about the dimension. We write a repetition loop where there is 2 dimensions or 2 billion dimensions. It's still the same software that is doing it. The challenge is when we are looking to complex problems like the machine vision using neural net to mimic the function of the human eyes, to understand what is inside the image, what is depicted by the image. That is the most difficult problem. And the complexity that people use in the neural net was helping them to get to that point that they can mimic the functionality of the human eyes. But for us, it's still the same, the repetition loop that we have to analyze the data. And at the FAA, we ask simple questions like, Did you know for sure that your system will operate correctly under this lighting condition, for example? Or did you make sure that your system can handle the... Should I speak louder? So we ask simple question, and in the traditional way, people were able to show that they could comply, but with machine vision, we are talking about millions of images, and if they ask us to go through millions of images manually to verify that they have data, that they train the system under different conditions, it's impossible for us to go through the data manually just to answer a simple question. So we use computer to analyze it. And again, we ran into a major computational issue that we could write a program to verify that. But as the dimension increases, the time it takes to finish the job increases exponentially. So the program could be verified to run with a dimension like 10,000 parameters. But as soon as we go over that threshold, the program would run forever with no indication when it will come to the stopping point. So that is the major challenge for us. But as far as analyzing the operating condition, I talked to people working on the most difficult problem of machine vision. So I asked them, can you provide information for each of the image that you have the operating condition from that image? And people said yes, but it takes a long time to do that. So I had to show some basic example. We talk about using convolutional neural net to process images. And the key thing about convolutional neural net is the convolutional layer at the beginning, where we use it to extract features or characteristics of the images. Right now, the machine learning practitioner just put it in as an extra layer of complexity to solve the problem. But I show them that if we use it to extract lighting condition, we can easily get the feature of that image in terms of lighting condition. We can analyze the sharpness of the image to infer the weather condition, where if you have foggy weather, your image will be blurry. If you have clear weather, your image will be sharper. We have the technology to extract them through convolutional layer before the neural net. So we show that if we can get through the computational layer challenge, we get to those where we calculate the characteristic that we ask from the operational domain. Then it's very easy to demonstrate that the system can work well under different lighting conditions, or under different weather conditions, or under different seasonal colors surrounding the environment. The technology is there, the computational efficiency of the computer is not there yet. So that is the key thing that we are pushing, and we like to talk to different researchers to present the problem that can help us. But the fundamental idea of verification of a machine learning neural net is there. It's just that it's so complex that even using computer might not get there for us in real time or in our lifetime. So that is the major problem that we have. To summarize, we saw one type of problem where people had complex physics base that describe their solution, but they cannot generate their solution in real time during operation. So they generated offline the solution and try to train the neural net to do the same thing. And in doing that, they sacrifice some accuracy, but they gain through computational efficiency. So that is one type of problem we saw. Another type of problem we saw is that the problem, they don't have any physics base to help them, but they do have extensive set of data to describe what is expected. And we follow the solution for verification of the first type of problem. We could apply to the second type of problem, which is mainly the machine vision, trying to mimic the human function, the human eyes function that no physics law could describe. But the verification is still the same. It's just different in terms of complexity and computational efficiency.
Thank you very much, Trung. So I would like to use the last 10 minutes for your questions. So I have a number of questions in my hand. I start with the one that that is really the controversial one. So while we're discussing here the simple models that we would like to certify, bring it to aircraft, the technology, the rapid pace of technology is not really waiting for us. So the innovation in AI is really fast. And how do we speed up the certification approaches, techniques, the safety of what is being developed to keep up with what is being invented?
So I'm in a commercial organization, right? We, as I said before, it's existential. We have to hit certain milestones on a certain timeline or it's the end of the company. So speed and efficiency is part of the DNA of what we're trying to do. And indeed, doing new things and getting them certified by a government agency with a history of the kinds of what's the word I'm looking for? I'm looking for a nice word to say slow. But deliberate, right? FAA has a deliberate process for a reason. We have an outstandingly safe aviation system, orders of magnitude safer than riding in a car. You are more likely to die by a heart attack, by choking, by a car crash, orders of magnitude more likely than in a commercial airliner. That was not an accident, no pun intended. That was an engineering and regulatory priority for over 50 years. And FAA is to be credited for so much of that. So the point being, it's not, ugh, it's so slow, we can't innovate. This is what we got for all that process, and we have a responsibility to uphold that safety record. And so when I say, from a commercial point of view, okay, how do we get more efficient at it? And when I say we need to focus on exactly what the burden is, what that assurance bar is, what I'm talking about is, how is it that we can demonstrate for this particular choice of this particular application in this particular scenario, what is exactly the bar I need to hit to meet that safety intent? And why do I believe that? And how am I going to convince this approver so that we both agree that this is a compelling argument for the behavioral predictability of the system? And that's what we're doing. And so to Darren's point earlier, we have these conventional methods that rely on traceability and structural coverage analysis and knowing what to test. Some of that breaks because we can't do traceability for machine learning requirements because there are no low-level requirements. You've learned it from data instead of decomposing it manually. And so that's both a blessing and a curse. We can't use that strategy anymore, but it shakes us up and say, hey, what are we actually trying to do? We're not trying to turn that crank for the purpose of turning that crank. We're trying to get a result. We're trying to get a result that the output of that process meets the requirements it needed to meet. We have a history of doing this way, but there are some other ways we can make that argument that this output meets this requirement. And so one of those is performance-based verification, which is something that a number of us are working on. And so, for example, using data analytics and other kinds of assessments to show that the way it behaves, regardless of how you implemented it, is actually what the requirements are asking for. And so a nice metaphor there is like, let's say you go have, surgery and neurosurgery, and the surgeon asks you afterwards, he's testing your hand. He's not going to look at all the neurons that he cut. He's going to ask you if you can make the fist when he's testing your hand surgery. So the performance-based assessment there is you can do the thing. And so performance-based assessment is one of the avenues for verification that we're starting to unpack and figure out how to build the foundations under so that we can make a different kind of argument that this output meets its requirements. No, not just an argument that because I did this process this way and I have this traceability, but also, and maybe sometimes instead, look, I can show that the performance meets this because I have, where we can make it, statistical or data analytics arguments that show acceptable performance under the circumstances. And so the commercial question of how we get faster, there's innovation in assurance too.
That's
figuring out new ways to make the case.
I think that comes a lot with the generative models, large language models. I see the questions. Many of the questions touch the base with the personalizing AI, right? So what we were discussing here, there are simple models, and there are complex models, and there are models that we think AI replaces human. And then now I see, how about we certify AI as a pilot? So why don't we I just read it, why don't we treat certification of AI systems more akin to the pilot licensing? Or the other one is, how about the public acceptance of AI? I think the public acceptance, the certification problems comes back to the AI agents that replaces human. I think on the one side, like in such a panel discussion, we're saying AI is an implementation method we apply to the known questions which are relatively low in dimensions that we can assure and then certify. On the other side, I think the question from the public is clear. What is the next step if we really have personalized AI? So I think that I would like to not skip this question, but ask this question. Okay, we know how to proceed further with AI as an implementation method, but what are your thoughts with the AI agent replacing human?
I think it's a mistake to look at things like human pilot certification as a good basis for an AI pilot.
Agree.
In fact, I'm sure we could probably get AI pilots that outperform humans at the certification level and then fail miserably as soon as there's an unexpected situation in the air, right? I mean, we see this in mathematics, right? But people here are probably familiar with some of the large reasoning models that scored silver medal in international level math competitions and yet failed to do basic arithmetic. It's not sufficient. I'll leave it at that.
Yeah, and when a pilot passes a licensing exam, that is not at all comprehensive. That is just a surface check of some particular hard problems and basic knowledge, but it also is based on a presupposition that there is a human brain that is taking that exam. And that's what we don't have in any of our AI agent-based systems, that they're not equivalent at all. There's a whole level of depth of knowledge that, however it's done, is encoded in a human brain that we're taking advantage of for free, in some sense, that is not going to be evident from an assurance standpoint. And certification is all about providing evidence, demonstrating that the system meets its requirements and doesn't do anything unexpected and that would be dangerous. That's why that's not an equivalent comparison.
I remember when I was young, I look at whenever I was sick, I was given medication, and on the bottle of medication, there was clear instruction from 0 to 6 year old, take 1 pill, from 6 to 12, take 2, and above, take 3. So I kept thinking that as soon as I learn how to learn math, to pull red in amount of medication, we're not going to need medical doctor anymore. So that's my dream. As soon as I learn mathematics, I thought I have a good computer program that can replace medical doctor. I still don't see any medical doctor being replaced. So now going to space application, we look at the Apollo program. So we saw the movie Apollo 13, where we saw astronauts surviving harsh conditions in space. And we asked ourselves, can AI survive that if we train them to operate the space capsule? And the people I talked to, they said that most of the AI program are below the level of intelligence of a monkey. So just imagine if we put a monkey in the space capsule of Apollo 13, do we envision those monkeys can survive that? And most of the time, people said no. So there is something unique about human intelligence that we don't understand yet. We know how to mimic some of the function, but we just cannot mimic the ability to improvise, to solve new problem. Even though I show at the beginning, we can partition a complex problem to simpler problem, but there is still something unknown that requires human intelligence to solve, and we don't know how we solve them, but we know that human intelligence can do that kind of problem that artificial intelligence cannot yet. So if we are talking about using AI to operate the machine, yes, we can train AI to operate a machine, but if we want to ask AI to replace human, to operate it safely, we're not there yet. That's my personal opinion.
Thank you very much. So I think the topic is very exciting, and then we can discuss it here another couple of hours without any problem, but we're bound to 75 minutes on the purpose that you see other papers and other presentations on this exciting conference. I would like to ask you to join me for an applause for our panelists.